Good afternoon. We are going to do Unit 10, Day 2, Simplifying Logarithms. And there's quite a few pieces to this section because the algebra with logarithms is not generally something that is covered in Algebra 2. So you're actually going to be learning some brand new algebra processes. If I could offer you one piece of advice, I would say memorize your log properties as soon as humanly possible. The earlier you memorize them, the easier the whole unit gets. Okay, so Roman numeral 1, let's start with basic logarithms. What are they? Okay, so basically a logarithm is an inverse of an exponential function. It's an inverse of an exponential function. It is commonly used in science and engineering, which is why we learn it. Engineering, excuse me, there we go. And basically logarithms are kind of a leftover of slide rules. Which calculated larger numbers based on logarithms. So if let's say that we have an exponent, y equals b to the power of x. This is your exponential form of an equation. In logarithms, basically the power goes on its own, and then you have your log with the same base as the exponent, so base b, it's a small subscript number, of y. And this is your log form. These two equations are actually the same exact equation. So they are the same equation, just two forms. And they're good for different things. The exponential form is the one that we tend to use for a lot of our algebra because the exponential form follows transformation rules. So when we were graphing with a natural log or natural base e, we were doing transformations to an exponential form. The log form doesn't follow transformation rules, so when we're trying to graph something, we have to flip it over to exponential form. Also, exponential form is easier to calculate without a calculator, because exponents are something we can calculate using basic algebra rules, whereas log must be switched over to that form. So there's some things that we can do in log form that we can't do in exponential form, and one of those is there are some simplifying moves that are better in log form than there are in exponential form. And that's the main reason that we even use log form. Largely, though, we will generally use exponential form for most of what we do for graphing and basic calculations. You need to be able to switch from one form to the other easily and know when you should use one and when you should use the other. That's not a formula. That is just what a logarithm versus exponential form means. So maybe this is something we want to draw a box around, so mentally you know this is something you should memorize, how to go back and forth. Okay, so let's do an example. We're going to find the inverse. We're going to find the inverse of an exponent, y equals 2 to the power of x. And we haven't done inverses for a long time, so I want to go through this one with you. So when you do an inverse, first thing you do is you switch the x and the y. So I'm going to make this into x equals 2 to the power of y. Then, when you're doing an inverse, you need to solve for y. Now, this is where you're going to want to use your logarithms to help simplify when it's convenient. So taking this equation and to get the y out of the exponent. So let's put that over here. Solve for y. We need to get y out of the exponent position. It can't be up there. This is where we use logs. So we are going to log both sides. And when you log both sides, you need to pick the same base as what you're working with. So I'm going to log base 2, the x, and I'm going to log base 2, 2 to the power of y. So to get y out of the exponent position, we have to log both sides and pick the same base. Now we're going to learn some of the properties that I'm going to show you, but this is why you need to know your properties really, really well, because as you can see, using the algebra rules that you already know, you can't get to the next step. It's not possible. And that's why we have to memorize properties, is to figure out what to do with this big mess. So one of the properties that we're going to learn is that the power can go to the front. So we have y log base 2 of 2. Another property we're going to learn is when you have log with the same base as the argument, it equals 1. So now I've got log base 2 of x, and we're solving for y, so just flip-flop the sides. Y equals log base 2 of x. So when you're finding the inverse of an exponent, the inverse is automatically a log. And when you're going for the inverse of a log, the inverse will be an exponent. So if you look at what we started with and what we finished with, you will notice that it looks a whole lot like the definition of a logarithm, which it is. Okay, so really quick, let's do some vocabulary. Again, you've got your exponent form, x equals 2 to the y, and then you have y equals log base 2 of x. Okay, so in the left one, the 2 is the base, and y is the exponent, or the power. In log form, the subscript 2 is still the base, but we have a new term, which is the x. Anything that's inside the log, and anything inside the log is what follows. If it needs parentheses, it gets parentheses, but that is what we call the argument of the log. It's anything inside. So we have base, and we've got power, base, and argument. Just a little vocabulary there. All right, flip the page. We're going to do properties of logarithms. And again, the earlier you can commit these to memory, the better off you'll be. Okay, so, excuse me, hit my camera. All right, so Roman numeral 2, properties of logarithms. And I'm going to give you the property, but I'm also going to show you how to figure it out. So if you can't remember the property, hopefully we get to a place where we can find it using another method. So here's our properties. Log base 2 of 2 is always equal to 1. If the base and the argument match, it's equal to 1. Log base 2 of 1. Anytime your argument is a 1, it's always equal to 0, no matter what the base is. log base 2 of 0. Anytime 0 is the argument, it is undefined. Log base 2 of negative 2, this is not even possible. Log base 2 of 4 is equal to 2. We'll go over that in a second. And then log base 2 of 1/2 is equal to negative 1. So if you have the inverse of the base, it equals negative 1. Now you can see how memorizing the rules can be a bit of a challenge. So I'm going to show you how to go through it for yourself. We're going to start with the log form. And then we're going to change it to exponential form. And that will actually get us where we need to go, which is what it is equal to. And I'm offsetting these a little bit because I don't want it to be completely hard to read. All right, so let's put this in log form. We want to know what log base 2 of 2 equals. So log base 2 of 2 equals some mystery number x. So first thing we're going to do is put this into exponential form. So base 2 to the power of what's on the right is equal to the argument 2. And I'm going to make the base 2 have a curl, the argument 2 not have a curl, so you know which one is which. Well, 2 to what power equals 2? X has to be 1, and that is the property. Okay, let's do the next one. Log base 2 of 1, we want to know what that equals. Again, put it into exponential form. 2 to the power of x. How is that possible that it's going to equal 1? Well, any number to the power of 0 equals 1. So x has to be 0. All right, log base 2 of 0 equals x. Flip it into exponential form. 2 to the power of x equals 0. Now, there is no way to make a 2 a 0 unless you multiply by 0, but it's not being multiplied by 0, it's being raised to the power of x. So 2 to the x equals 0 is undefined. Or in the case of graphing, that will be an asymptote, but you can't get a 0 from a 2 to the power of x. 2 to the power of 0 equals 1, but there's nothing you can raise it to the power of to make it equal to a 0. All right, let's do the next one. Log base 2 of negative 2 equals some number x. Flip it into exponential form. 2 to the power of x equals negative 2. Well, just like the last one, there's no way to make 2 to the power of x a negative 2. So this is actually not possible. You say, what's the difference between undefined and not possible? Undefined means an asymptote. Not possible means it is mathematically impossible to calculate that. It's like, what does the color blue smell like? You can't smell a color. You can't have this equal to a negative number. It's simply not possible. All right, moving on. Log base 2 of 4, we want to know what that equals. So 2 to the power of x equals 4. Flip it to exponential form. And obviously 2 squared is 4, so x has to be 2. And this one is actually closely related to the log property. I guess I could just add this on. I don't know why it's not in this set. If you have log base 2 and it's to the power of, it's got an exponent like that, the exponent can go in the front of the log. So that's another property we'll be working with. Last one, log base 2 of 1/2 equals x. Okay, switching it to exponent form, 2 to the x equals 1/2. 1/2 is 2 to the negative 1. So x has to be negative 1. Now, a way to use this property to get to the answer is to rewrite this as log base 2 of 2 to the negative 1. Then the negative 1 moves to the front. And anytime a log base 2 has an argument of 2, that equals 1. So you can actually get the same thing just using a slightly different method. Okay, so those are the properties of logarithms. We're going to do lots of practice with that. Okay, Roman numeral 3. Change of base formula. Now there's a couple reasons you're going to want to change the base of a logarithm. Typically, you're going to want to change the base for easier calculation. You might want to change the base because on your calculator, on the face buttons, it has a base 10 and a base E as a face button. So if you change it to base 10 or base E, you can use the face buttons on your calculator. And then, of course, change of base formula can be used for simplifying multiple logs, which we'll get into later, but basically to simplify logs together, they have to have the same base. Okay, so what is the formula? Let's say you've got log base A and B is in the argument. So let's say that you want to have the new base. Let's say n is the new base. To change this to a base n, you have to split the log into 2 logs. One on top, log base n of the argument b, and one on bottom, log base n, and then the base a becomes the argument a. That would be your formula. And again, generally with a new base, you're looking for a base 10 or a base e because they're the most convenient. All right, let's do an example. We're going to take log base 2 of 3, and we're going to change it into a base 10, and then we're also going to change it into a base e. Okay, so let's do the base 10 first using the formula. It's going to have a log on top with the new base, which is 10, and the argument of the old one, 3, over another log base 10 on the bottom, this time with the old base now in the argument position. If you do a base 10 number, you have the option of writing the 10 or not. If there is no base written, it is automatically a 10. So log 3 over log 2 is automatically base 10. That's our default. Now for base E, you have to use natural log. So when the base is E, log, regular log, becomes natural log. So natural log is lowercase ln. If you're writing natural log, the E is implied. And this would be of 3 over natural log base E of 2. And again, natural log 3 over natural log 2 is automatically a base E. You say, why isn't it NL? Well, because I believe it was French, logarithm naturel, and so that's how it got translated that way. So your base E is natural log, which is abbreviated LN. You'll notice on your calculator you have a natural log button and you have a log button. The log button is base 10, the natural log button is base E. And that's how you change the base. Okay, Roman numeral 4. Expansion properties. Expansion properties. Okay, first one, we're just going to use log base 10. So log of 3 times x. If you have two things multiplied together in the argument, you can separate them into log 3 plus log x. Okay, property number 2. You've got a log, let's say you have 3x to the power of 4. Now to do this, to make this work, the entire argument has to be raised to the power of 4. It could not be log of 3x to the 4th and have this work. It doesn't work. It has to be the entire argument, in which case the 4 goes to the front. 4 times the log of 3x. And if there's no parentheses, anything after the log is assumed to be in the argument. All right, log of 3 over x. If it is a single fraction, you can separate it into log of the top, log 3, minus log of the bottom, which is log x. If you're asked to expand a log, it means you need to get rid of, so when you expand, there needs to be no powers, and everything on the inside must be monomials. So if you were being asked to expand number 2, this first step is a good one, but then you would have to separate out the 3 and the x. Now since there's a 4 in the front, you would factor it out and then do the first property, log 3 plus log of x. And then you would distribute 4 log 3 plus 4 log x. So no parentheses either. So that's what it means to expand, is to write it with no powers and no parentheses, and only monomials on the inside. So one single term on the inside. I guess we should write on the inside. All right, those are your expansion properties. By the way, they all work backwards. So they all work backwards. You can go the other way. And the opposite of expand is condense. And if you condense, you simply do the reverse property, and your answer would end up being log of 3x to the 4th, which is one term, no scalars. That's condense. Okay, Roman numeral 5. Log conversion properties. All right, so, and I'm mainly just wanting to give you examples of these. The basic ones seem to be where people get stuck. So they want to know what log base b of 1 is equal to, and they'll show it to you like that. So one of the ways you can help jog your brain is to write it log base b of 1 equals x. Then you're going to flip it to exponent form, so b to the power of x equals 1. And anything to the power of 0 is 1, so x equals 0. Let's do another one. Log base b of b, what does that equal? Again, when you write it, put the x in to help your brain. Switch it to exponent form, b to the power of x equals the argument b, and of course, x would have to be 1 to make that happen. Now this one is honestly, I would just memorize this one as a property. The algebra in it is like 7 steps long. It's b to the power of log base b of y. And honestly, I would just memorize that if the base of the exponent matches the base of the log, and the log is in the power, it's equal to the argument. And again, there is algebra that can go with that, but it is just super heinously long. So this is one I would just commit to memory. It will make your life a lot simpler. Okay, so I've given you all of your log properties, and now we're going to actually start to use those log properties. So I'm going to do some examples. So this is Roman numeral 6. We're going to do examples to get you in the mood of things. Okay, so example 1, let's say you've got log base 3 of the square root of 3. Now, in order to do this, you have to remember how to write a square root as an exponent. So, square root of 3 is 3 to the power of 1/2. Remember that 1 is the power on the 3, and 2 is the root. So then we're going to use our property that says if you have the argument raised to the power can come in the front. So 1/2 log 3 of 3. And we know that if the base and the argument match, it equals 1. So you can see how you're going to use your properties until you can actually calculate it. Example 2. Let's say you have log and the argument is 1 over the square root of 100. Now automatically this is a base 10 log because there's no base written, so it's automatically a 10. You know that the square root of 100 is 10. So this is log of 1/10. Now you don't want to split it into a log over a log. That will just make it worse. What you do want to do though is switch this to exponent form. This is log of 10 to the negative 1. The negative 1 goes in the front. So negative 1 times log of 10. And since log of 10 is a base 10, anytime the base and the argument match, it's a 1. So your answer is negative 1. All right, example 3, solve. Log x equals 3. So to solve this, you need to get the x out of the argument. So this is an automatic base 10. So I'm going to put this into exponent form. And I'm going to put the 10 in here just to remind you, it really is a base 10. It just doesn't have to be written. In the beginning, you might want to write it. So to solve this, I'm going to flip to exponential form. This is 10 to the power of 3 equals x. And 10 times 10 times 10 is 1,000. So log to exponent, exponent to solution. Let's do another one. This is the same thing, solve log base 2 of x equals 5. Go ahead and pause the recording and work this one out for yourself and then restart. Okay, so you solve this by flipping to exponential form. 2 to the power of 5 equals x. And 2, 2, 2, 2, 2 is 32. If there's more than one log and you're solving, you need to get it to a single log first. That's your first thing. And then second, then go to exponent form. And then third, actually solve. So if they do give you more than one log, use your condensing formulas to get it into one single log that then you can use exponential form. Okay, so last one. And for some reason, this just gets people, and it's not that hard. Anytime you want to graph a log. So graph a log, and we're going to do f of x equals natural log of x without a calculator. Okay, so when you want to graph a log, the problem with natural log is that we don't have a way to calculate it without a calculator. So what you're going to want to do is change to exponent form for your points. Okay, so y equals natural log of x. Of course, natural log is a base e. So switching it to exponent form, e to the power of y equals x. Okay, so now that we've got it into exponent form, we're going to use that form to get our points. So we're going to do, and you're going to do this backwards from how you would normally do it. So remember, if y is 0, then x is e to the 0. And we know from memorization, anything to the power of 0 is a 1. If y is 1, x is e to the 1, which is about 2.7. If y is negative 1, then x is e to the negative 1, which is 0.4. So we can still use our 3 memorized values. It's just that the calculation goes backwards. All right, draw yourself a pair of axes. Now, when you graph a log versus an exponent, because remember the original one is a log, the asymptote is vertical. This is x equals 0, and this is the asymptote for log equations. Now, if I plot my 3 points, 1, 0, 2.71, so 2.7 up 1, and 0.4, negative 1, you can see that when you do a log graph, it's infinitely close to the asymptote, then it curves and it slowly gets steeper without ever actually going vertical. And there is your log graph. So remember, when you have to graph a log, change it to exponent form to get the points, and you have to really kind of pick the y's first, and then calculate the x's second. And that's how you get your points with your 3 values. All right, I think that's enough information for today. Have a great rest of your day.